Take what you learned in the last 3 lectures. You are prepared. There's a lot of work and a lot of logical steps between them. Really, that describes pretty much. That really describes all of Bayesian inference and a great deal of the kinds of methods that are being used to analyze cosmological data. And so I've focused on the concepts. I tried to really make it very clear so that the foundations are good. And so what we're going to do now in the next hour is to bring it forward and talk about applications on real data and talk about examples for how and techniques for how to work with these elements that you have been, that I've just shown you in the last 3 hours. Some people asked me for lecture notes, and so I sat down over lunch and wrote these notes. No, I'm joking. I had written these before, but if you want to download some partial notes that describe multivariate Gaussians and how to do inference with multivariate Gaussians, how to denoise. There's another example in there. There's also some more information, some tricks for using Gaussian random fields, and also some information of how to go beyond Gaussian random fields, how to for example, calculate moments of functions of Gaussian random fields, how to transform Gaussian random fields. So these are not supposed to, these are still at the draft level, so they're not for very wide distribution, even though, of course, this is now being broadcast around the globe. So they're still labeled as draft, so use them with care. So we talked about Gaussian random fields really as a mathematical object, and I gave you some justification for doing that at the level of saying, okay, Gaussian PDFs are the least informative PDF that you can specify if all you have is the mean and the covariance. But in cosmology, we're actually in a pretty special situation, special place, because it's almost unique, I think, across the sciences that we have a physical system that really physically predicts extremely Gaussian fluctuations. And so when we talk about a quantum field on a shallow potential in gravity, quantum fluctuations in the field source density fluctuations, potential fluctuations, and therefore density fluctuations in the metric. And so I have a little cartoon of that. Let's see if this works. See, this is roughly, so in a scale-free way. That's one model. There are other models for producing these. The point is that that we actually have a physical model that says that these fluctuations are Gaussian to a very, very, to very good precision. And so this Gaussian field stuff that I talked about is an extremely good approximation and can be pushed very far for cosmological observables, like, for example, the cosmic microwave background. And I'll show you an example in a minute. So let me put this in context. So if we have some mechanism that sets up in the early universe, sets up metric perturbations, then I can make a 3D map of these metric perturbations. And so if I make a cartoon, space-time cartoon, so if we're here and we look, so this is our past, and then there's an equal time surface that our past light cone intersects, then what I'm plotting there is this part of it, because that's everything that can influence whatever we observe today and whatever we measure today is in this patch here. This patch has the geometry of a ball, because I've suppressed various dimensions. I know it looks like a disk, but it really is a ball because I've suppressed some dimensions. And here I've plotted this ball. And we sit at, so the point that's labeled U, really it's labeled U in the past, it's this point here. So it's your world line that, our world line. From the beginning of the universe until today is a straight line on this plot. You've chosen coordinates to make this all nice and conical here. This is the object that sources all known structure in the universe, anything that you observe. And so that's the one time something random happened in the universe on macroscopic scales. And after that, it's deterministic evolution. That is what we find. We don't really find any evidence for creation of structure after this early epoch here, where inflation would, or some other mechanism, whatever the mechanism is, would occur before. So this time going upward. Space being in this plane, for example. So then we have a fundamental object, these random numbers, and they tell us about the mechanism that forms structure in the very, very early universe. And to several of the models that we have, in several of those models, these perturbations really are extremely Gaussian. So what we observe, when we look out into the universe, we see various observables. We see the cosmic microwave background. We see the distribution of matter in the universe that you've just heard about, and all the other wonderful things that you've had lectures about in the last weeks. This is my cosmic cone, where we are here and today, and all these various observables here along the light cone, and on the other side, some of the milestones in the evolution of the universe, from the end of inflation until dark energy domination today. So all of these observables somehow derive from this initial set after, with some radiative transfer, gravity, astrophysics, transforming that into observables. This is my kind of picture of cosmology. So one way of looking at what cosmology is, to observe these observables and then make inferences about this Gaussian random field here. And of course also the various bits of physics that transform it to the observable. Let me skip this. So let's go to an example that uses this Gaussianity and uses the toolbox that you have now, that I've given you in the last 3 lectures. So, for example, for standard inflation, imagine that you set things up in the beginning so that inflation, anyway, all the conceptual issues with inflation, let's ignore those. We just say we have a slowly rolling scalar field in some nice flat patch where inflation occurs and ends, and then we get initial perturbations that are very, very nearly Gaussian, and then it turns out the anisotropies in the CMB temperature and polarization are linear maps to a very good approximation of these initial perturbations. Linear maps. What is a linear map? Well, a numerical realization of a linear map is a matrix. Okay, so we have CMB is equal to linear map of initial conditions, and surely there's going to be some noise in the observation. Seem familiar? Okay. So how does this help us? Well, it helps us because we know how to solve this problem. So let's use Gaussian random fields to build a linear physics time machine. We take our CMB sky to be our data, which I call Y here, and let's say we want to reconstruct one slice of this primordial ball of potential fluctuations. Let's call that X. Here's what we've written down just a few hours ago. Okay, this block thing, X, Y, so the observable Y is, and the thing we want to reconstruct, X, block covariance, and then here are the equations that you now know and hopefully love. But you can just use these formulas for the conditional density of X, the thing we want to reconstruct, given Y, the thing we can measure, to build the optimal inference of x given y, because everything is Gaussian. Right? So you can do this. This is these are the papers where we introduced the machinery for this in roughly 2000, published in 2005. So here's again a cartoon version of the previous slide. Here's the CMB map, and then in some patch here, for example, we can reconstruct various slices. The little animation that you saw there was actually the reconstruction for simulation of many slices. So let me do this again. Start the animation. You see it sort of changes, and that's because we can actually, using temperature and polarization, we can reconstruct several of those slices around the time of recombination. So by inverting, by solving this inverse problem. Right? I didn't say the words inverse problem, but obviously Bayesian statistics is often about, you know, doing an inverse problem, trying to find something we don't know from something that we can measure. And the reason why this works is exactly this linear transformation, the fact that I can write this as a matrix A. So here I exhibit the actual linear transformation. So in general, I can write the most general linear transformation would take my primordial potential or metric perturbations phi, I take the Fourier modes, and then I have a sum over k here, or integral over k, and this is the most general linear operation I can write down that takes a k-index object into an Lm index object, where Lm is the spherical harmonic coefficient of my sky map. But we have a homogeneous and isotropic universe, and we can work our group theory, okay, the fact that it's rotationally invariant on average, and the statistics are rotationally invariant and shift translationally invariant. And that means that this general linear operator has to have this special form. Okay, so it factorizes, and there's a function here, L functions of k only, and then there are these mathematical functions called the spherical harmonics. And that is why you have heard so much about the CMB, because the CMB is small, linear perturbation theory is extremely accurate, and so you have so this really is a good representation of the data. Linear map. And the map A here has this very special form, which means it's easy to compute and to apply and so forth. And here is, this is a bit of personal history here. This is actually the first time, so this is the result, okay, when you do that. This is with temperature, the temperature Planck map. This is Smika from Planck 2015. And you apply nothing other than that conditional density, conditional mean equation for this problem. It's nothing else, okay, just that. And you reconstruct a slice basically through the middle of the epoch of recombination, okay? And these are our primordial perturbations. These are the quantum fluctuations that sourced our structure in our universe as reconstructed from the CMB. There's a little line across here because there's some contamination, galactic contamination here, but this stuff out here is very clean. And you can actually sort of see, just to comment, you see it's got some large-scale features, and then the sort of small-scale features. It doesn't have power in all scales. I don't know if you've looked at these, if you've looked at CMB power spectra for a long time that are almost scale invariant. They have the little bumps and wiggles, but mostly are 1 over L squared. This doesn't look like 1 over L squared. The simulation I showed you before actually has perfect 1 over L squared. This doesn't, because it turns out the CMB is actually blind to some ranges of scales, because it turns out the transfer functions go through 0 for some L at the time of recombination. And so those we cannot reconstruct, but still, I mean, this is the best possible reconstruction you can get. But it turns out that nature is kind to us. So again, we're fortunate. I don't know if you were at Rashid's lecture. He was pointing out that for cluster cosmology, there are very fortunate coincidences that make it possible to do it. Here we're fortunate that we have temperature and polarization. And so when you take temperature and polarization data together, it turns out the polarization transfer functions are just out of phase with the temperature transfer functions. And so then you start filling in much more of the information. And this is the result of rolling the cosmic quantum dice in the early universe that started off, all structure formation in our universe, as seen through the CMB, inferred from the CMB. So this is what we just did. Okay, just exactly the equation that you have, measured quantity, inverted, etc. So this is a Wiener filtering type operation. And, well, it's not in disguise, it's an example of Bayesian inference. And in general, so this is a specific case of Bayesian inference. I showed you how we went the other way in the lectures. We started going from the Bayes theorem, and we showed that if you assume that all of these, that the joint PDF is Gaussian, all the conditionals are Gaussian and all the marginals are Gaussian for Gaussian. And so that all of this is, every piece of this is Gaussian, and so that's why we could write the equations on the previous slides. In the general case, this slide here recalls this naive sampling algorithm that I talked about at the end of the second lecture, I think it was, where I said one way to do Bayesian inference is just to have an infinite number of forward simulations, and you only take those parameters that resulted in a forward simulation that exactly matches your data. That's just this slide. So this is a correct in principle, and I think instructive way of thinking about it, but for actual implementation, it is typically impossible. There is something called approximate Bayesian computation. It's a subfield of Bayesian. So it is Bayesian statistics, but the technique for doing Bayesian statistics is basically this algorithm, except rather than checking whether the real data is exactly equal to the simulated data, you put in some flex. Okay, you put in an epsilon. You ask whether you want the simulated data to hit near the real data. And then you have a chance of it actually working. It's still inefficient. Actually, if you have time, we'll get to techniques that we've developed very recently, something that I've been working on for the last year or so, year and a half, that actually do something like this and actually make it very feasible, and in some cases faster than the other methods I will talk about now, which means you only have to simulate forward simulate to do the inference. So what is typically done, which I haven't talked about yet, is, and I'm sure many of you have heard about Markov chain Monte Carlo, or Metropolis Hastings sampling. That's what the MH is for, Metropolis Hastings, where you've written down your prior. You have written down a probability distribution for your likelihood, okay, based on some model equation. For example, your data might be have some mean, which is some function of your underlying parameters, plus some noise. This is often a typical model. So if you're modeling the CMB at the level of the power spectrum, for example, you would take this as the mean spectrum predicted for some cosmological parameters, plus some noise, which implements the fact that, of course, a given measured power spectrum would have some uncertainty on it. So this is the kind of model that's in the Planck likelihood. For example, when you're doing the Planck likelihood, it looks a bit like this. It's actually Gaussianized, so the noise is assumed Gaussian, even though in actual fact the statistics are non-Gaussian, but for high L, that's a good approximation due to the central limit theorem. Okay, anyway, so often it's like this. So you write down a Gaussian here with this mean and this covariance coming from some fluctuation, or some other, it could be chi-squared, if you're looking, it could be, if you're looking at counts, you have a Poisson, maybe a Poisson distribution where you say, as a function of my parameter, my data is a number of counts where the intensity of the photon counts, for example, is a function of some parameter of my model. It could be photon counts as a function of frequency for a line. If you're measuring some kind of spectral line, it could, so this could be Poisson, Gaussian, any of the other standard distributions. And then you have a function to evaluate. So you have your P of theta given d, which is proportional to this. You forget about the normalization because it turns out you don't need it for this. And then you just go around, evaluate this, but you can evaluate this function as a function of your theta. So the advantage of doing it this way is that your data is fixed here, so you automatically, in my favorite diagram, hopefully yours too now. So if this is your joint PDF, you have your measured data, and by putting the data in here, and fixing the data once and for all, and then varying this as a function of the parameters, you automatically live on this slice. Okay? So in the naive sampling, you're filling this whole joint PDF, and you're only keeping those that happen to hit on the slice. So that's where the inefficiency comes in. Here, you fix the data to start with, and you explore this function as a function of theta automatically on this slice. How do you explore that function? Well, you could just grid it. Okay, if you have one parameter, two parameters, just make a grid, search through the space, see where this function has support, where it's very small, where it's large, you search through. It turns out that for more than 2 or 3 at most parameters, it is more convenient to look at this not as a function evaluated at parameter values, but to look at this, but to explore this in terms of samples from it. It's a PDF. We can sample from the theta, and then we have a sampled representation, and the density of those samples actually is the value of the PDF. And in order to generate samples of general functions of a general form, like this, one algorithm is called the pretty fundamental algorithm is called the Metropolis-Hastings algorithm. It's a very simple 2-line code that says, assume that I am somewhere to start with. Okay, here's the, so this is now in theta 1. This is not my favorite diagram. This is a diagram where I have 2 parameters, and I want to sample from these 2 parameters, let's say. So let's say I start off somewhere, just pick a point. And then I say, okay, I now have a way of producing a proposed next sample, usually somewhere in the vicinity of this point. It could be a Gaussian centered here. Okay, I draw from a Gaussian centered on my current point. Let's say it ends up there. I then calculate this so-called acceptance ratio, which this is my P of theta here, theta vector, theta 1 and theta 2. Okay, this is supposed to be a vector here. Okay, I then calculate the ratio of the probability density here to there of my target density. Okay, that's here. And then depending on what I use to propose, I sort of have to correct for any biases due to maybe the proposal always tends to go to the right or something like this. So I have to make sure that I correct for that. That's this ratio here. If it is a Gaussian, then it's always symmetrical, and that Q ratio, the ratio of the proposal PDFs, actually goes away. And then the algorithm is that if this acceptance ratio is larger than 1 or equal to 1, then you accept this proposed move. Otherwise, you accept with probability A. A is always positive. It's only got positive stuff in it, so it's between 0 and infinity. If it's less than 1, then you interpret it as a probability, and you accept that proposed move with probability A. That means there's a chance that the next point in the chain is just again this point, if you don't accept it. If you do accept the move, then you move. If you don't accept the move, you still move, but you still have another point, but it's going to be there. Okay, that is the standard workhorse algorithm, for example, used in CosmoMC, many other packages for doing Markov chain Monte Carlo in cosmology. So the problem of this, or the difficulties that you encounter when you do this in practice, is that it can be inefficient if this proposal Q is suboptimal. So the whole art of doing Markov chain Monte Carlo is to find good proposals that have give you a large chance of accepting the next point, the proposed point, but also get you around the space in an efficient way, so that you don't just kind of explore some tiny region and you miss the fact that there's a large region of high probability density somewhere. And if the number, so this is fairly easy to do, so the Gaussian works really well if you have 10 or less parameters, and if your target PDF has a single peak and sort of a connected region of high probability density. But it can get slow when the number of parameters goes up. Basically, sometimes you have to take a very short step in order to have any chance at all of getting accepted at the next step. So here's an example. For example, if you try to take very large steps, what happens is that, let's say I'm here and I try to take very large steps. So I draw from a large Gaussian like this. Let's say I try to propose this point here, gets rejected, I stay there. Propose this point there, gets rejected. Propose this point there, gets rejected, and so forth. Maybe I propose this point there, it still gets rejected. Eventually I propose this point, okay, then I move. So what happens when you try to make very large steps, especially if you have a larger number of dimensions than 2, is that you can tend to get stuck in one point until you finally find some place that you can move to. So then this is the trace as you do the walk. Basically, the walk just keeps hitting on the same point, ding, 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 until eventually you accept a move and then you jump. Then the jump can be quite large, but then you're going to get stuck there again until you find a good point, etc. If you have a too small a step, so here I initialized the chain. The PDF you can see has support kind of in this range, but I initialized it very far outside. So you can see that for a very small step size, you move every time, basically, almost every time, but you only ever move a very small amount because you're only proposing very locally. So you're proposing nearby, okay, you move. You propose nearby, yes, you move. You move, you move, you move. But then you generate a chain, okay, that takes a very, very long time to get anywhere. And this is what happens here. So you get a very strongly correlated chain. And this is for something that is close to an optimal step size, where you move a reasonable distance every time, but you also have a high enough probability to move. You can diagnose this by looking at the chain of samples that you generate as a function of sample step, and calculate this autocorrelation, and you'll find that there's some near-term correlation that's going to decay, and if that decays very slowly, that means that your chain isn't working very well. Okay, so this is just a short introduction to Markov chain Monte Carlo. There are an infinite number of resources online, for you to look at this and learn about this, but these are the main salient features. Now, in the case of the cosmic microwave background, where we have a map on the sky, doesn't really matter that it's a sphere, but we want to find the power spectrum of this. So when you want to do parameter inference for cosmic microwave background map, your likelihood looks like this. Okay, you have a prior on your CLs. Maybe you say that, we know that they're not infinite, because otherwise we would be frying from all the power of radiation coming from the sky, etc. So there's some prior, and then there's the likelihood that says that the data, the CMB sky map, is going to be drawn from this Gaussian here, which has a signal covariance, which is parameterized in terms of the power spectrum, plus some noise covariance. So the data is signal plus noise, where the signal has this covariance and the noise is this covariance. So you've seen actually an example of this today in the lecture. The problem is that if you want to do Metropolis Hastings, there are many, many problems. One of the problems is that when you, or even if you want to grid it or whatever it is that you want to do, the problem is you have to, for those methods, you have to evaluate this in order to compute the acceptance ratio. And evaluating takes a very long time because this is a large matrix. The Planck maps have roughly 50 million pixels. So you have the 50 million by 50 million matrix. Even if it's just a million, you can do a quick calculation that it takes about 10,000 CPU years to evaluate this once. So you cannot evaluate it, even though it's just a simple determinant, but determinants scale like n cubed, where n is the number of pixels. So Metropolis Hastings is impossible. Gridding is even worse because, in fact, you have to grid it in 1,000 dimensions. A 1,000-dimensional grid has, if you want to do 10 steps in every grid direction, you have to evaluate it 10 to the 1,000 number of times. So you can forget about that. So that's why Markov chain Monte Carlo is very important, because it allows you to explore even high-dimensional PDFs, because a grid doesn't get you anywhere when you have a large number of dimensions. It's too costly. So the solution for this case was Gibbs sampling, which is another sampling technique, where instead of writing the data directly as if, in this likelihood that we wrote there, you split up the likelihood into two pieces. One where you say, okay, my signal is drawn from the signal model, which is a Gaussian with covariance given by the power spectrum. And then the data is drawn from around that signal with some noise. So just split this up, and I introduce the signal map as well. So I have a data map, I have parameters which are the power spectrum, and I have a signal map. So I have two sets of parameters, signal and power spectrum, with the data set. And it turns out that when you split a PDF like that into two subsets, because it's possible to draw from these conditional densities here, that you never need to actually evaluate the PDF. When you can draw from the conditional densities, this is called Gibbs sampling. And what you do is you, let's say you have your signal here and your power spectrum there, and you have some PDF here. It's going to be non-Gaussian, but it turns out, so let's say I start here. So then, given my signal map, now it's easy to do power spectrum estimation because I have a perfect signal map. I just calculate the power spectrum of it. And I need to add some fluctuations in a certain way, but that means I can easily sample from this conditional posterior, which is P of CL given the signal. Let's say that n puts me here. Then at the next step, I'm going to sample from P of the signal given that CL and the data. So the conditional density for the signal given the CL and the data. This is also given the data, but of course, if you have a perfect signal map, you don't need the data anymore. So you remember this concept of conditional independence? Given the perfect signal map, I can forget about the data. It's not going to add anything. Because I have a perfect signal map here, my last sample of the perfect signal map, which I got from the data, assuming the signal covariance given in terms of the power spectrum. This here, by the way, is like Wiener filtering. So you do a Wiener filter operation, getting a reconstructed signal map from the data for a known power spectrum. That moves you in this direction. Let's say it jumps over here. And then once you have that reconstructed perfect signal map, you then do a sample and you then say, okay, what power spectra could have given rise to that perfect signal map? And that puts you there. And so you iterate that, and you jump, etc. It turns out by iterating that, you generate samples of pairs S and CL, which are samples from the joint posterior, so for the posterior of S and CL given the data. That's Gibbs sampling. Doesn't matter. Doesn't matter. You can actually, well, I don't have time to prove it to you now, but it turns out that this
you can think about this also as Metropolis Hastings, and it's just that your proposal densities are these conditional densities. So you can only apply this if you're able to sample from these conditional densities. If you can do that, you can show that the acceptance ratio is always 1. That means you never actually need to evaluate anything, and that saves you, 10,000 CPU years a pop for the. So this is the only known way. That's not true. There's since been other techniques that I will talk about in a minute, but this is the first way that was shown to do exact statistical analysis of the power spectrum and the signal map given a CMB dataset. So this is used in WMAP and Planck analysis. So here's another, basically in a block chart, a flow chart picture of what I just said. Basically, you start with your isotropic Gaussian process prior. In other words, that's your model of the signal CMB, that it's just a isotropic random field with a power spectrum. You then, let's say you start off with some guess of the power spectrum. You then Wiener filter the sky. You add fluctuations, basically sample from the posterior for the sky. This is called augmentation. So this is just sampling from the posterior for the sky, for the signal given the data and the current power spectrum guess. Then you compute the power spectrum from that, and then you feed that back in. And so this is so the power spectrum move you in this direction, the signal move you in that direction, and you can just iterate that. It turns out the conditional density for the power spectrum given a signal map is something called the inverse gamma distribution, something you can easily sample from. So this is, in some sense, it's a nonlinear Wiener filter now, because in the Wiener filter, I had to assume the signal covariance. Remember, I had to assume the prior, the C theta theta. That was assumed known. Here, you're learning that prior from the data as well as doing the reconstruction. So you're letting the signal covariance change and the data change at the same time. So this is quite powerful, because it's actually, let me just skip this, because you can do this for large scale structure data analysis as well. Guillaume Lavaux and Jens Jascher have been doing work along those lines. There is but here's an application to radio interferometry. I know radio astronomy is a big thing in India, so I thought I put in this example where you have a set of telescopes that are working in interferometric mode. There again, you have a data model, which is just like the one I wrote down earlier today. So you have some signal. Each telescope has a primary beam which focuses on some patch of the sky. They all focus on the same patch of the sky, and then you correlate their integrated signals with the phases, which basically means that you're measuring in the Fourier domain. You're measuring the signal here. This is the pixel-based domain, angle-based domain. And then I can look at, these are the measurements in the Fourier-based domain. This is what that signal looks like here. And the data look like a sampled version of this, because as the sky rotates, and for the various pairs of all of the telescopes that I have looking at the sky in their particular configuration, I then sample this UV plane in a certain pattern. And you can see that the data model again looks exactly like what we had before. So it's the signal which is then modulated with the primary beam, is then Fourier transformed and is then sampled, partially sampled in this Fourier transform. So that's and then from that data in the UV plane, you want to get back to the signal here. So again, another example where, I hope you've now start feeling like the hour this morning was well spent, because you've now done CMB analysis. Now we're doing radio interferometry, reconstruction. And so you can then use this to reconstruct general images. This is interesting because For the CMB, we had a physically very well-motivated model. I'd be the last to claim that Einstein's face is a Gaussian isotropic random field. But it turns out that even with an image which is clearly not a good representative of the prior is Gaussian, homogeneous Gaussian random fields. So apply a beam that focuses on the central region here. I then sample this with my interferometer pattern. I have my UV plane, Fourier transform, sample the the UV plane, so the plane of visibilities in the Fourier plane. And I can then do the reconstruction. And these are different methods. This is the input after applying the single telescope beam. This is the reconstruction from this partially observed UV plane, so it looks pretty good. This is what a high-performance version of the standard method of radio interferometry does. So you can see it introduces artifacts. It's called the clean algorithm. Actually, it's a modern update of the clean algorithm. Yes? Yeah. No. Maximum entropy method uses some attempt to regularize, because if you do this if you just try to solve a least squared reconstruction without any priors and so forth, you take a flat prior, you get a horrible thing coming out. So here we've taken, we've set our priors that this is a Gaussian random field, but notice that we actually also infer the power spectrum of Einstein's face at the same time. So we do exactly the CMB analysis, this nonlinear Wiener filter. This is important. Because that actually means that the combined model turns out to be non-Gaussian. It's Gaussian if you fix the power spectrum, but if you also infer the power spectrum at the same time, the effective model is actually, you have a non-Gaussian model, and that's why this works so well. The method you're describing is a yeah, I can talk about more about that later, but basically it's an asymptotic limit of a different kinds of prior, where as an image prior, you choose to say that your prior images drawn from the prior are images where monkeys throw bits of light on a screen. Okay, just random. You have n blobs of light, and you throw them onto the screen. If n is large, then you can show that the maximum entropy, or that an entropy prior is an approximation to that, and that's what some people use to regularize this inversion. What we show here is that this Gaussian field approximation with this nonlinearity built in, where you actually infer the power spectrum as well, does far, far better. This already does far, far better than the maximum entropy version, by the way. So, okay, so you can quantify this. Of course, because we're doing Bayesian analysis, we don't just get one image out, we don't just get one reconstruction, we get a PDF of images, right? We get the full posterior PDF. So what we can then do, for example, is here's the original image area, and we can calculate the reconstruction variance. Okay, we take all these samples that we get, we calculate the variance per pixel, and so we can then say, for example, that in this range here, the variance is low, and so we choose. So in this range, we're very confident that the reconstruction is good. As we go farther away, we get less information, etc. So this is one of the advantages of Bayesian modeling, Bayesian inference, that it always comes with a full characterization of the uncertainties. So let's go further beyond. So what if Gibbs sampling? So Gibbs sampling can only work if you know how to sample from these conditional densities. So this will not work in all generality. It works for certain cases, like this case that we just discussed, where you do Wiener filters and you then sample from the covariance using an inverse gamma distribution, and you keep iterating that. There's something called Hamiltonian Monte Carlo, which is an extremely powerful method, and that is general as long as you can differentiate your model. That means as long as your model of the data is differentiable all the way through in terms of your input parameters. So what is Hamiltonian Monte Carlo? Who's heard of Hamiltonian Monte Carlo before? Okay, some small set. Okay, good. So this is new for a lot of people. So let's take your, I've written P of theta. I don't mean the prior here. I'm just abbreviating. This is the posterior. Okay, this is my target density, the thing I want to sample from, which is P of theta given the data. Okay, I'm dropping the given the data. I take the minus the logarithm of it, and I think of that as a physical potential, okay, of a particle moving in a potential. Okay, now I'm thinking Hamiltonian dynamics. I know it's kind of causing a collision in your brains right now. Okay, two different parts of your brain are now talking to each other. The part that is trained to learn about on classical mechanics, and the part that I hope I've just opened up in the last three lectures. So it turns out you can connect them, and it's just a trick where you think of these parameters as the position in a Hamiltonian system. And you then make up, so it's one of those things where, so you have this P of theta, you write it as this logarithm there. So my P of theta now is equal to is proportional to e to the, this psi of phi potential minus. And then I'm just going to add another set of parameters, independent, okay? So let me call them pi. And I'm just going to give them a Gaussian, I'm just going to multiply those two, so independent, multiply them, and just going to say they are Gaussian distributed with some covariance m, the zero mean. Okay, then you stare at this, and you think, this looks suspiciously like e to the minus h of theta and pi, where h is the Hamiltonian. This looks like, p squared over 2m. Yeah, so it looks like the kinetic term, and this looks like the potential term of your Hamiltonian. And then you think, so what do I do then? And then you say, well, I guess I can do Gibbs sampling here. So first I can sample my pi's. That's easy because it's independent, so I just sample from a Gaussian. I know how to sample from Gaussians. And then at the next step, I can sample from this. And so here's the clever proposal. You sample a new set, sorry, actually you don't sample just from this. You sample from this full thing with the sampled momenta that you just generated. And the proposal for the full thing here is that you say, I start off at some position, oh, this is not the right diagram. Okay, here's my parameters 1 and 2. I guess I could have left the, okay. And I start at some position here, and I'm now going to integrate my particle, my position here, as if this was Hamiltonian dynamics in a potential, to some new point. Okay, so I just solve Hamilton's equations, Hamiltonian dynamics, in a potential that is given by the log of my posterior PDF that I want to sample from, with the initial momenta that I drew here at this point. Okay, so I end up, after some time of integration that I have to pick, I can pick that as I want. I end up at some other place here. And so now the question is, okay, that's my proposal density. My proposal is that sample. And do I accept it, yes or no? So the amazing thing is, because I'm integrating Hamiltonian dynamics and the symplectic structure of Hamiltonian dynamics, we know that for a Hamiltonian that does not explicitly depend on the time parameter here for the integration, which it doesn't, Hamiltonian is conserved. It's energy conservation. That means this is going to be the same here as there, which means that the ratio of final probability, proposed probability density to initial probability density is equal to 1, guaranteed by, the gods of mathematical symmetry. And then what about this proposal though? Remember, I had the ratio of the targets, and then I also had to correct for the proposal ratios. Well, the wonderful thing is that Hamiltonian dynamics is time reversible. So I could have very easily started here and rolled back to there the same way. So due to the time reversibility, in fact, the proposal is symmetric. And so in other words, Hamiltonian conservation guarantees acceptance probability of 1. Then you get these pairs of theta and pi. You know, every time you do this, you propose a new momentum, you kick the thing, it rolls, you get the new point, you kick it again, it rolls in some other direction, you get the new point, you kick it again, it rolls there, and so forth. Of course, to write down the equations of motion, that's why it has to be differentiable, because it's the derivative of this with respect to theta. Okay, that gives you the force for the equation of motion. So this has to be differentiable with respect to theta. That's what I meant with the model has to be differentiable. And then, since you're sampling from this joint PDF, theta of part given d, sampling from this joint PDF, but then because you're really only interested in theta, remember you only made up the pi's to give it the structure, you just simply ignore the pi. You just marginalize by ignoring those, and you just look at those, and that does the integral over those. Okay, just ignoring this coordinate. So if you have, there's going to be a pi coordinate in this direction, okay, in this direction, but you just look at the projection onto this plane, and that gives you a sample from your from the target density that you wanted to sample from, typically posterior density. This is a lightning fast introduction to Hamiltonian Monte Carlo, but really it's this the smart part about it, and it's sort of the magic in it is this the fact that it's set up. It has an easy way of adding these extra parameters, which in the end don't hurt you, and that allow you to evolve this in such a way that you always get acceptance probability 1. This is extremely useful in high numbers of dimensions, where it's not at all clear that you get, you know, any sort of reasonable acceptance probability with other kinds of proposals. Very hard to design them. So there are many applications of this now in cosmology. I think this was one of the first, Amir Harjan, in 2007, where he wrote on a cosmological parameter sampler. Power spectrum inference, this is the other way of doing CMB power spectrum inference that's not Gibbs sampling, that is also exact, uses this. Large scale structure, so nonlinear cases. This is Gaussian still. This is now log normal PDF, so this does work in non-Gaussian situations. Okay, this is not just quadratic, it can have any form, as long as it's differentiable. We wrote a case for non-Gaussian initial conditions. So when the initial conditions aren't Gaussian, but you have a non-Gaussian aspect to them, the Gibbs sampling goes out of the window. And so you do non-Gaussianity analysis, you can do it this way. You can do dynamical reconstruction, which I will show in a minute, of large-scale structure data, which is very non-Gaussian, right? Clusters and so forth. It's not a Gaussian random field. And CMB lensing potential reconstruction, which I'll just show very briefly. If you want to learn more about MC using Hamiltonian dynamics, look at this. Radford Neal is also one of the pioneers of this technique. So just as a quick flash of a result that we've been working on very recently, which is B modes for the CMB, okay, gravitational wave, imprint of gravitational waves on the cosmic microwave background, which is seen, which is masked by lensing, okay, so you have lensing reconstruction. So you want to know what the lensing potential is for obvious reasons. Traces the mass of the universe, mass distribution in the universe, but you also want to know what the B modes are, and those two kind of are interfering with each other over a range of scales, in large scale, a range of scales. And so here's the true lensing potential. This is the true E mode and the true B mode, and then the data. Actually, I don't have a picture of the data here, but the data basically looks like this, because the B mode is completely mixed into E through the lensing. Or in other words, sorry, the other way around. The E mode gets mixed into B through the lensing. Lensing couples E and B. So B looks like that because this is so much bigger than this. And then in the reconstruction, in the reconstruction, it turns out you recover the lensing potential, you recover, this is for a masked sky, so this is the edge of the mask here, you recover your E, and you recover the B based on basically this kind of the statistical features. You see this, this is kind of in the case where the signal to noise is just at the edge of being able to discover B. And these are the samples in the chain using Hamiltonian Monte Carlo. You see that the uncertainty in my phi reconstruction here is shown in this fluctuation. Okay, this shows the uncertainty in the phi reconstruction, uncertainty in E. Clearly, when you mask the sky, you don't see that part, so this fluctuates as uncertain. And you see that B is quite uncertain, but when you average all of those together, you see some detection of B, in this patch here. This is a simulation, obviously, but another example of Hamiltonian Monte Carlo, which I mentioned at lunch, discussing with some people, is a full forward model of for a galaxy survey, which we call Borg, the Bayesian origin reconstruction from galaxies. We start with the Gaussian prior on the metric perturbations, the potential. Then gravity moves matter forward into filaments, clusters, creates voids. Then we say the galaxies somehow derive from this underlying matter distribution, non-linear, non-Gaussian matter distribution. And then we model the survey in terms of the survey geometry, for example, like this, right? The selection function of the survey, the number of galaxies, the bias, so there's the mask, all this stuff. And then what we want to know is what was this initial perturbation, the initial density distribution that gave rise to the structure that we sample with these galaxies in the sky. So this is a quite detailed sort of hierarchical model. I haven't used the word hierarchical model yet. Hierarchical model simply means that I sort of have several layers in the model. I start with this density distribution, then I have gravity, then I turn that into a galaxy density, then I turn the galaxy density into a natural sample of galaxies in my survey. And Borg really is just an implementation, just took us 10 years to write, an implementation of Hamiltonian Markov chain Monte Carlo that reconstructs, that does an inference. It samples from the posterior for this initial density fluctuation given the final observed galaxy positions. So here are the samples of the initial density. When you average those together, you basically get like a nonlinear, non-Gaussian analog of the Wiener filter. Okay, this is the observed region. You get some information here. You can also look at this today, which gives you a reconstruction of the nonlinear matter distribution sampled by the galaxies, which uses as a model the full forward gravity collapse of structures. So it's not just sort of smoothing in some way, in a generic way, but it actually does, it says, okay, if there's galaxies here, 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 and there, and a cluster here and a cluster there, then with absolute certainty there has to be a filament connecting this, because we know that this is generated through the collapse of cold dark matter. So let me show you a movie of what that gives for the Sloan Survey. That didn't work. You see. Okay. So here's a slice through the Sloan Survey. The full survey is in there. This is the main sample. We are here at the tip of this. As we go out, this is the nearby universe. We go farther away. These are the edges of the survey. Okay, we only look on some part of the sky. As we look out, these are not observed. This region here is not observed. And so what we get are samples of the initial conditions that under gravity evolve in these final conditions, which are then compared through a bias model and the survey model, and this, with the actual data, actual galaxies in the sample. And what you see, obviously we don't just have the beginning and the end, we have everything in between as well, because it's a physical model that we're fitting to the data here. these are the initial conditions. And if you stare at this long enough, you realize that there are stable features in here. Okay, so like there's underdensities, overdensities. The fact that this moves says that there's some uncertainty. Here's the final redshift, so the current time slice, and you see, for example, that even with these sparsely sampled galaxies here, you see that, you know, for example, I'd be happy. Remember, this is about betting, right? Posterior tells you the betting probabilities. In all of our samples, for example, we see that there's a filament connecting across here. Okay, there's a few galaxies here, but just due to gravity, there has to be a filament here. I'm willing to bet, you know, give this extremely high odds, etc. Yes. That's right, because here it's unobserved. So there's a lot more fluctuation here. Like, for example, in some samples, there's a cluster here, in other samples, there isn't a cluster there. There's a void there. So I don't have information there. It's basically, this is a set of possible true dark matter distributions given this data set. Okay, so out here, I'm basically sampling from the prior, because it's not constrained by that data set. But as I get closer, for example, here, there's a void that actually is outside of the observed region. And I'm willing to bet a significant amount of money that if you go there and observe, they will find a void there, for example. Okay, so to finish up, I'm a little over time. Unfortunately, there's a part of this that I wanted to get to, which I will probably not have the possibility to get to, but just to give you, this is the power of forward modeling. That's why I'm spending some time on this. Every single sample gives you an assembly history of all the structure that we see in the sky. So this is a sample of initial conditions from the prior, of the initial density distribution evolved through cosmic history. And here in color are the observed Sloan galaxies. So you see them, they fall exactly in the right place. You can do, because we have full dynamical histories, we can actually make maps of the velocities at the current time. So here, this is the Sloan Great Wall. So you see stuff is falling onto the Sloan Great Wall. The color is radial velocity, but you see other features. So you have dynamical information. Basically, this says, given where these galaxies are, given that we have Lambda CDM, these have to be the velocities. And we can even do things like follow the Lagrangian phase space sheet of the dark matter. Dark matter is a thin sheet in phase space because it's cold, so it will ramp up as matter collapses. And this is colored in as the number of sheets, like the number of folds in the sheet, that the number of streams, dark matter streams at any given point in the Sloan Survey. So you see inside overdense regions, you know, the sheet is pretty tangled up. Inside void regions, there's only one sheet, so single stream regions. Because this is actually fully nonlinear, we can look at the assembly history of nonlinear objects like coma cluster. You know, this is the way stuff flows onto coma. We can get the coma nonlinear mass profile. So the line here and the range, obviously, is Bayesian statistics, so you get probability distributions for everything. So this is the reconstruction with our nonlinear model, and these data points are completely external data points, for example, using velocity dispersions or using lensing information about the mass profile. And so here we're really testing Lambda CDM, because given Lambda CDM and the observed galaxy distribution, we say this has to be the mass profile. And then we go and check it through other observations, and it turns out you get something that actually fits. Nowhere in the code did we tell it that there's a cluster there. I mean, we didn't say, here's a cluster, it has a radial profile. It's just, you know, here are a bunch of galaxies. What does the mass have to be? And we find this result. Okay. I have about 15 minutes more material. I leave it to the organizers if I should stop now or not. This would be a good place to stop. At 5. So we have a bit of flex. 10 minutes? Yeah, okay. All right, so because I mentioned Are you okay with that? You want to hear about simulation-based, fully likelihood-free simulation-based inference? This is the part where we're trying to realize this naive and impractical thing of doing just forward simulations until you find things that look exactly like your data. So we call this, I call all of this kind of stuff, I categorize approaches to doing large-scale structure inference as avoid, adapt, and attack. Okay, avoid is you just don't do it, you do CMB, everything's nice and Gaussian and linear and easy. Adapt is you try to find certain features that are maybe easier to model. That's what most of the field is doing. And then there's attack mode, which is kind of what the previous part of the talk also was about, the lecture, where you try to model absolutely everything. You model the non-Gaussianity, you model the non-linearity, you model all the physics, you put everything into the model, and you see what that implies. So here's another kind of approach that is in that spirit, where we start from this equation that should now seem very familiar to you. This is work I did sort of over the last year or so, prepared about a year and a half ago or so, with these collaborators, so many of which are or were at the Flatiron Institute. That's why the logo is there. I spent my time in New York last year. So, what if we can only do simulations? So the idea is that if we are not able to evaluate this, we don't know how to write down a likelihood. I already gave you some ideas how to write down likelihoods, Gaussian, Poisson. But what if your data doesn't fit into these nice categories? What if you have a complicated data set that has a complicated distribution that maybe you can simulate in a computer code, but you don't know how to write down, some closed form PDF? So let's say we are in that limit. We have a prior, and we can simulate given parameters, but we don't know how to evaluate the likelihood. We don't have a forward model, we don't have the full analytical form of the likelihood, or even a numerical one to evaluate. So here, likelihood-free inference 101. This is, again, it's a bit familiar. It's basically the naive model, so I'm going to go through it quickly. So the idea is you draw from the prior, you get a bunch of parameters out from that. You do some simulation, so you run your large-scale structure simulation. You then summarize that in terms of your simulated data, some features of the simulation, and then you look at the measurements, power spectrum, number function, whatever it is that you measure in the sky, and you compare the simulated values with the true values, and if they're equal up to some epsilon, you accept, else you reject, and you do another simulation. That's the naive, what I call the naive sampling approach, except for the fact that you have an epsilon here. So you accept within some neighborhood of the true data. Of course, if you make that neighborhood large, then the samples, that will degrade the quality of your comparison, but it will increase the number of accepted samples. So there's an optimization for how big to make that neighborhood here. But as the size of the neighborhood goes to 0, this will approach, the samples here will become samples from the posterior density. Yes? I didn't hear you. What is what? Rho? Oh, sorry. This is a distance that you have to, if you want to define a neighborhood, you have to define some distance between the simulated data and the true data. So it could be squared difference, but could be some other distance function that measures how far away is the simulated data from the true data. Okay, and if it's the same, then you accept, or if it's within some epsilon. If the epsilon goes to 0, then these samples will become samples of the posterior density, assuming that these summaries here contain all the information about the parameters. Okay, so of course, as I said, it's not very practical if you have a high-dimensional data space. So if you have your full 3D simulation with 100 million voxels, you're never going to find, just from a random forward simulation, it's not going to suddenly look exactly like our universe, right? So in order to have any chance of that happening, you have to reduce the dimensionality of the data. and you have to figure out where to do the simulations to increase the chance that the simulations that come out look like what we measure in our universe. So the compression, it turns out, so this is the first idea here, is that we can use massive compression to reduce the dimensionality of the data. So let's say we have our parameters. We do a full forward simulation of cosmic structure. Then we go in and we summarize this in many different ways: power spectrum, number of functions, bispectrum, trispectrum. I don't know, you come up with it. Void probability function. Just make a long list of M summary statistics. Let's say if M could easily be 100 or so, even in a 100-dimensional space, it's hard to hit a point in a 100-dimensional space. The simulations have to hit the data, right? So, but then it turns out that you can always, in general, compress these M summary statistics into a smaller set of compressed statistics where N is equal to the number of parameters. So if you have 5 parameters, you can always find 5 compressed statistics out of these summaries that contain all of the information in those M about these parameters. This can be proven. There's these information inequalities, and it turns out you can always choose some combination of the data in such a way as to saturate this information inequality, which means that at that point the variance in the parameters will not be larger if you use these compressed quantities than if you use all of the summaries. This is explained, if you want to learn more about this is explained in this paper here. Okay, then how to explore the exploration. So instead of trying to hit the point, we actually instead, what we do is we take our favorite diagram, theta d, and instead of just trying to hit near the data with our simulations, we actually go into the space, in this compressed space, and then actually estimate this joint density here from our forward simulations. So we draw from the prior, we do forward simulations, we get a bunch of points here, and we assume that this is not a crazy PDF with lots of widely separated peaks with crazy structure. Often it is just some kind of blob in large numbers of dimensions. And then actually, the nice thing is in that case, because there's regularity here, even those simulations that don't hit near the data actually inform you about what's going on in the neighborhood. Okay, so you actually don't throw any simulations away. You use all of them to construct this joint PDF. So and we model this using a Gaussian mixture model. So just as a sum of multivariate Gaussians. This is in this paper. So there are examples of this. This is an example for supernovae. Let me just skip over this, just to show that this is a case that you can do in the traditional way. We do have a likelihood for this case that we explore with a very, very long Markov chain to make sure we get the exact posterior. And then this is what we get with our technique, and you can't see the difference because they're on top of each other. So exactly the same. The Markov chain took several 100,000 samples. We used about 10, for this case, we used about 10,000 forward simulations. So actually much fewer forward simulations than likelihood samples. So it turns out this is actually faster than the Markov chain. So what if you don't have what if you think you might have missed something in that list of M summary statistics? What if you think I haven't captured all of the information in those? I know that information I can compress down to just a number of parameter elements, but I could have much more information. How do I get the rest of the information? And so now we're getting to machine learning, or like at least deep learning applied to this. So in this paper here, we say that we can train a neural network in such a way that it finds combinations of the data that maximize the information in those summaries with respect to some underlying parameters that we want to measure. So there's a neural network that's trained through reinforcement learning to compute functions of the data that maximize the information about the parameters of the model. And this generates nonlinear informative summaries that we can use to constrain the model parameters. Here's how this works. So you have a neural network, okay, where that you're feeding in. So you choose some parameter point as your fiducial model. You feed in data simulated for that fiducial model into the network, and you ask the network to output a small set of summaries here. You also feed in for every parameter, you displace the parameter a little bit, and you feed in simulations at the displaced parameters, positive and negative. And you generate a bunch of simulations where you always, let's say if you have 5 parameters, you put in the fiducial parameter itself and then the displaced parameters. So you need to run a set of simulations. These are all unconstrained forward simulations. Out of these outputs, you can compute the covariance of these outputs, and using these displaced values, you can actually compute the derivatives of these outputs with respect to the input the parameters you want to constrain. Those give you the Fisher information. The Fisher information is a way to express what the information content is of this data set about the underlying parameters. And so we then change the weights and biases of this network. We optimize the network to maximize this information. Okay. So here's an example. So some of you have been talking to me about how do I learn from just noisy data like the CMB. It's just a bunch of noise, and the information is all in the variances. It's in the power. It's not in the actual values, right? So this is the simplest possible example like that you can do. Let's say you have a bunch of numbers, 10 numbers, and you want to, and they're drawn from a Gaussian, and you want to know the variance of those 10 numbers. Any linear summary, any linear combination of those numbers would always lose a lot of information. The 10 numbers, if you make one number out of them, that means you only basically have 1/10 of the information left. The full information about the variance in this problem you can calculate, it's 5. Okay, so any linear summary can give you at most 1/10 of that. Here's what happens with this neural network. You start the training process, you calculate the Fisher information as you train. You see that very quickly it finds that it has to compute, it finds a function of the data that it computes that has information 5. 5 amount, Fisher information is 5. The blue is the training set, and then there's a validation set, which you see overlaid there. So the network finds a summary statistic that has high amounts of information. In fact, maximal information about the underlying variance. And so what we can then do is for a bunch of different variances, theta, we can start doing forward simulations, simulate our data, apply the network, the trained network to the data. Those are those green points here. So for a bunch of forward simulations, we get that. And then we have a data set, which we also apply the network to. That gives you this value. And then this is exactly this diagram here, right? So for different input parameters, we do forward simulations. And then we ask which forward simulations hit the data, the value, the summary of the data. And those are the purple points. And so in the histogram, we get this purple histogram. And for this case, we can do the Bayesian analysis exactly, and that's the orange line. And you see that it actually recovers exactly the posterior. So in other words, this network, without ever taking Statistics 101, has figured out how to compute summary statistics, actually a sufficient summary statistic from the data and trained in an automatic way using only forward simulations. Anyway, I'm going to skip over this. So now we have noise. This was with signal only. This is signal plus noise. This is, which we could also do exactly. It works. This is a case where we actually have signal plus unknown noise. So the noise variance is also changed from a stochastic model. This part I don't know how to model exactly. So we had to do a lot of Monte Carlo simulations to get this, get the theory curve. The network figured it out in like 20 seconds. We have examples. So for more information, look at this paper. We do an example with Lyman alpha forest inference, where we have a Poisson sampled thing of a nonlinear transformed Gaussian, and we try to get the variance of the Gaussian. And this is the true value, and it finds the true value. And then there's an example for gravitational wave chirp. The code is public. And okay, let me stop here. Thank you.